All right, well, welcome to another wonderful day of trigonometry. We're going to have some fun today, hopefully, show you sort of a different way of looking at the world that ends up being really, really useful, lots of different ways. But before we get there, let me just open it up to any questions about what we've been talking about or any homework sets. And I know that Juan, you said you had something.
Yeah, I have a question on one of the homeworks, the chapter 9 review,
Okay,
number 22.
let me write that down here. Okay, so chapter 9 review number 22. Are there any other homework questions? We can make a list here before we go and find them.
I guess number 3 for the 9 review. There's just no video to explain what to do, and I haven't been able to figure out what to do yet.
Okay. Thank you for that, Adam. All right, so why don't I go ahead and share my screen, and we'll go ahead and go find those homework problems and take a look at them. All right, so hopefully you guys can see my screen here. So we'll go to chapter 9 review. And this is definitely a good time to be working on the chapter 9 review. I mean, obviously it's due today, but our exam next time will cover a big portion of chapter 9. So, but let's go take a look at these guys. All right, so let me just write down what these guys are, and then we'll go to the board. So we've got -6 times the sine of x. And we're going to add to that 1 times the cosine of x. And we want to write it as a sine of x plus v. Okay, so that's number 3. And then the other option, the other question that was asked for was 22. So let's take a look at this one, see what this is asking us to do. So for this one, we're just trying to solve this equation. Let me go ahead and write it down here. It's 2 cosine of 3x is equal to 1. And it's asking us to find the ones that are between 0 and pi. We're going to find all of them, but then we'll talk about how we can figure out which ones are between 0 and pi. Okay, so I've got these guys written down. Let me go ahead and quit sharing my screen, and we'll go to the board.
All right, so I've got the first one written up here at the top where we're going to combine a sine and a cosine, and we're going to make it look like a single sine. And this is kind of cool thing actually about waves is that when you put them together, when you take 2 different sinusoidal forms and put them together, you actually get a third one. If any of you are planning on taking physics when you get to 2nd quarter and you talk about waves and superpositioning, you will definitely see this where you put them together. All right, so really the question is, how do we figure out what the amplitude of the resulting wave will be? And then the kind of phase shift we would need for sine. All right, well, here's what I would do. I would start with sine of x plus phi and think about how that expands. So let's use that sum of angles identity. So again, let's just not worry about that. Yeah, we can leave the a here. We have a sine of x plus phi. That's going to equal a times. And so if we go and we look at the sum of angles identity, we see that we get sine of x times the cosine of phi plus the sine of phi times the cosine of x. So that's the sum of angles identity. I'm going to go ahead and distribute that a through and just rewrite this a little bit differently. So we're going to have a cosine of phi times the sine of x plus a sine of phi times the cosine of x. So that's what it looks like on the right-hand side if we use that sum of angles identity. All right, so far so good? All right, so now at this point, here's what we can do. Look at what we want it to look like. We want it to look like minus 6 sine of x and plus 1 cosine of x. Well, that tells me that this right here, a cosine of phi, is going to have to equal negative 6. Right? I want that multiple on sine of x to be minus 6. So that multiple is right now a cosine of phi. I'm going to set that equal to minus 6. And then similarly, over here, I've got a sine of phi times cosine. Well, I need that multiple to equal 1. So that gives me a cosine of phi equals 1. So whatever a and phi are, they have to make it so that a cosine phi is minus 6 and a cosine phi, or sorry, sine of phi is equal to 1. All right, so really all I did was I used that sum of angles identity to see what this form has to be and then related it back to what we started with. And this now gives me a system of equations. I've got 2 equations with 2 unknowns, and so I need to solve. And how we're going to go about this is probably easiest to do substitution. Like if I solve this guy for a, this first one for a, I get a is equal to minus 6 over the cosine of phi. And I can take that and actually put it into the other equation for a so that I get minus 6 over the cosine of phi times the sine of phi equals 1. Well, sine over cosine, I know that that's tangent, so I get minus 6 tangent of phi equals 1. So the tangent of phi is equal to minus 1/6. So we now can figure out what phi is equal to. Right? How would we actually answer that? How would you figure out what phi equals?
We just use inverse.
Yeah, you just use tangent inverse. Now, tangent inverse is going to give you one of many phis that work. Remember that whatever that gives you, it's going to be the angle that's between minus pi over 2 and pi over 2. But if you don't want that one, add any multiple of pi and you'll still get it. Okay, so in terms of what phi is going to equal, I'll go ahead and just write that up here. We know that phi is equal to the inverse tangent of minus 1/6. Now, obviously, yours might have different numbers, so watch for that. But at this point, you do inverse tangent. That'll at least get you decimals that you can type in. All right, well, we still need to figure out what a is equal to, but we can get that right here if we substitute back. So we're going to get a is equal to minus 6 over the cosine of the inverse tangent of minus 1/6. And because we can, let's try to simplify that. Let's kind of remind ourselves how that worked. this was that good old draw yourself the right triangle, make the tangent, figure out what the cosine is. So think about an angle here whose tangent is 1/6. So opposite over adjacent is going to be 1/6. We can use the Pythagorean theorem to find the third one. So the third one is going to be the square root of 37. Right? 1 squared plus 6 squared equals this guy squared. So since 1 squared plus 6 squared is 37, we get here. And we're looking for the cosine of that. Well, cosine is adjacent over hypotenuse. So the cosine of phi is going to be 6 over root 37. But again, that's plus or minus. So we'd have to figure out whether it's positive or negative, but the trick there is to figure out which quadrant we're in with phi. So remember that the tangent is negative, so that's either quadrant 2 or 4. But since we're using inverse tangent, that forces us to be in quadrant 4, because inverse tangent only gives us quadrants 1 or 4. So we're in quadrant 4, and in quadrant 4, cosine is positive. So that's what the cosine of phi is going to equal. So then my A value, if I do -6 over that, so remember A was -6 over root 37. Well, if you invert and multiply, that gives you minus root 37. So for this specific one, we're going to find that phi is the inverse tangent of -1/6. And A is minus root 37.
Got it.
Okay. So if we used a different phi, though, I just want to point out that had we used a different phi, like this one I told you gives you the one that's in the 4th quadrant, but I said if you don't like that one, you can add any pi you want. You do have to be careful with that, though. If we choose a different angle, it might change the sign on our A. Right, because this cosine could end up being the -6 over root 37. And because of that, I just go with what they give me. If I want to adjust it later, I can. Like this one, you may want to adjust because normally we don't like having a negative out front. We can avoid it. And we can avoid it easily, right, with a phase change. It's just going to have to be half the period. And you can take that into account, but I recommend that you just go with it as it is. Anyway, but sounds good. Sounds like we're feeling better about that one, Adam.
Yeah, absolutely. Thank you.
Okay, yeah, you're welcome. You know, and the fact that we chose sine was completely arbitrary. We could have chosen cosine instead. And obviously it would have led to a different phi. We would have gotten the same A though, because cosine and sine, the only difference is a little bit of a shift, right? So regardless of whether you go with sine or cosine, you're going to get a root 37, either plus or minus, but the phi would change. And in case people didn't see, Juan just put up in the chat a link to a YouTube video. He said that he found it that was helpful for this problem. So you guys can go back and look at that as well. Anyway, kind of cool though that you can combine any two sines and cosines and get another one. You can get another wave. Tends to be really, really useful in lots of places in physics. So. All right, so any other questions on that one before we go and look at the number 22? All right, well then let's go look at number 22. Let's tackle that one. So for 22, this was another one we just wanted to solve. So we've got 2 cosine of 3x equals 1. And they specifically said find all of the x's that are between 0 and pi. But like I said, we're going to go ahead and find all of them and then just figure out which are the ones that are between 0 and pi. All right, so in general, what do we want to do when we want to solve a trig equation? What's the process?
Separate the cosine by itself.
Yeah, get that cosine by itself. That's where we always want to start. So we'll go ahead and divide everything by 2. So we get that the cosine of 3x is equal to 1/2. So be careful. Don't. I know that this is a mistake that happens a lot. When we divide by 2, sometimes people will divide the inside of the cosine by 2 as well. Don't do that. Whatever's inside the trig function is inside the trig function. It doesn't interact with stuff on the outside. Okay, so now that we're here, we can use our inverse cosine. We basically need to figure out where is cosine equal to 1/2. So one of the places where cosine is going to equal 1/2 is going to be in the first quadrant, right? Since it's positive, we know that cosine is positive in the first quadrant. And the value that gives us 1/2 is pi over 3. All right, so that's one of them. The other place where we're going to be equal, get a cosine of 1/2, is going to be in the fourth quadrant. So we need an equivalent fourth quadrant angle. And if we look at that, or we use reference angles or whatever, we get 5 pi over 3. So those are the two places, pi over 3 and 5 pi over 3, where we get cosine equaling 1/2. If you didn't remember pi over 3, you could use inverse cosine, and inverse cosine will give you the pi over 3, but then you have to make sure that you go and find the other one using reference angles. All right, but before we solve for x, remember always, 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 when we get this angle, we need to add on to it a multiple of the period. So I'm going to put plus 2 pi n. Because not only pi over 3 works, but anything that's coterminal to it, and I can get that by just keeping adding 2 pi's. So remember that n is just any old integer you want. So 5, -6, 312, doesn't really matter. All right, so there's still one more step to do though, and this is we have to get x by itself. So we're going to go ahead and divide each side of this by 3, and the same thing with the other one. And so for this first guy, we get that x is equal to pi over 9. Pi over 3 divided by 3 is pi over 9, plus 2/3 pi n. And similarly, the second one gives us x equals 5 pi over 9 plus 2/3 pi n. So there's a list of all of the angles. Okay, so there are a ton of x's that make this true. These are all of them. But now let's go and actually answer their question, which is find the ones that are between 0 and pi. All right, well, we can start making a list. So let's just start with this first one. And we'll start with n equals 0. I'm not going to bother with any negatives, because if I take away 2/3 pi, I'm now going to be in the negative range. And since I need values that are bigger than 0, I'm not going to bother with those. So let's start with n equals 0. Obviously, if n equals 0, we get x equals pi over 9. So that is between 0 and pi, so that'll be on our list. If we let n equal 1, excuse me, we're going to get pi over 9 plus 2/3 pi. Well, if we get a common denominator, that's 6/9 plus 1/9 is 7/9. Okay, so we're going to get 7 pi over 9. And Bella, I just saw your comment. I'll get there in a second. And then continue. The next one, I would add another 2/3 pi or another 6/9, which would give me 13/9, and then 19/9, and so on down the line. Okay, so those are the ones that come from the first. From the second one, similarly, I'm going to start with 5 pi over 9, and then I'm going to add 2/3, which is 6/9, so that would be 11 pi over 9, 17 pi over 9, and so on down the line.
Quick question.
Sure.
So I was able to calculate the first two. I got the pi over 9 and 5 pi over 9.
Sure.
But then I couldn't get the third one. Was I just supposed to plug in 3 for n to get that third one then?
Well, let's just look at which of these are between 0 and pi. So clearly pi over 9 and 5 pi over 9, like you said, those are the two that you got.
Yeah.
But then the next one on our list, if you look at 7 pi over 9, that's less than pi, because it's only 7/9 pi, right? 7/9 is less than 1. But then everything else on that list is too big, more than 1 pi. And also on this list, everything from 11 pi over 9 over, those things are bigger than 1 pi as well. So in terms of finding that third one, like the first two, you can actually find those just by figuring out that pi over 3 and 5 pi over 3 are your angles and dividing by 3. But the other one, we have to find it by adding that 2 pi n and going through the process and solving for x, right? So that gave us this 2/3 pi n. And the way you find those is literally plugging in 1, 2, 3, 4, and so on into those n's. How far you're going to have to go, like how many times you're going to have to plug in, really depends on what interval they tell you, right? Like this one, it said 0 to pi. It turned out there were only 3. If this had said 0 to 2 pi, well, that would have added on 3 more of them, because 11 pi over 9, 13 pi over 9, 17 pi over 9, those are all less than 2 pi.
Okay, that makes sense. Yeah, because sometimes they ask for like the 4 least positive or something
Sure.
like that.
Yeah, and that's kind of where I'm getting at, is that depending upon what they ask you, you're going to have to go down a certain distance on this list, which is why I like to, even if they didn't say it, I like to find these expressions right here, which is all of the solutions, right? What I'm circling here in red, that's got all of the solutions, every single one of them. And now if I need to, I can make that list and I can find the ones that are relevant to whatever the issue, whatever the problem is having me do, which out in the real world, right? And the real world with this is going to be something sciencey, most likely. You're going to know which ones you need from context, right? And so by finding all of them, then you can adjust pretty easily to finding the ones they tell you.
Okay, that makes a lot more sense. Thanks.
Yeah, you're welcome. Okay, so Bella asked earlier, and let me jump back to this. She said, can I explain or describe why 5 pi over 3 was a value? Okay, so let me just make sure, Bella, you're good with the pi over 3? Thumbs up. You saw where that came from? Yep, okay. So the pi over 3, yeah, no big deal. Now the 5 pi over 3, that one came from the fact that since cosine is positive, I have to be in the 4th quadrant, right? So this right here tells me that there's going to be one that's in quadrant 1 and also one that's in quadrant, sorry, not 3, 4. So I'm just using the good old positive negativeness of quadrants that we talked about way back when. So I'm searching for a 4th quadrant angle that has the same symmetry as pi over 3. So if you go to the unit circle, let me just erase this part right here. If you go to the unit circle, so we were at pi over 3. So that was our pi over 3. We need the one that's down here that's got the same symmetry. So what I know is that this has a reference angle of pi over 3, right? Because it has to be the same deal. And so in the 4th quadrant, the way that you can get your angle in the 4th quadrant is by taking 2 pi minus your reference angle. So maybe you remember, hopefully you remember at least at some point we discussed that idea of how you can find the different angles in the different quadrants, and they're all based on the reference angle. Like in the second quadrant, it's pi minus the reference angle. In the third quadrant, it's pi plus the reference angle. In the fourth quadrant, it's 2 pi minus the reference angle. So I just got a common denominator here. So this is 6/3 minus 1/3, which is 5 pi over 3. So that's kind of the process there, and I just saw your thumbs up, so it looks like you're good with that. But this is also one that's on our chart. Since it's a nice angle, you could actually just go down the list. So Mariola, you just said you happen to have the same question, and only pi over 9 is the correct answer. So you mean when you tried to plug the other ones in, it didn't work? Did you put them in the right order? Because it specifically says they need to be, if I recall correctly, going from smallest to largest. So you might want to go back and just check real quick and see if maybe you didn't put them in the right order. So it should go pi over 9, 5 pi over 9, and then 7 pi over 9. So hopefully that will take care of that for Mariola. But while she's trying that, any other questions about this one? Okay, good, it worked. I figured a lot of times what it is just the formatting of your answer. Often they ask for it in a very specific way. All right, so any other homework questions before we kind of move on to the next topic? I do want to just check with Kiva, because I know that you started asking me something at the very end of class last time. You're good? Okay, cool. All right, well then we're going to go ahead and start moving on to the next section. And the next section is one of my more favorite things in Trig, and it's actually super useful later when we get to calculus. So let me just switch here.
Because I'm tired of talking to a screen. That's why I'll talk to you. So what we're going to do today is basically look at the plane, the XY plane, in a slightly different way. Basically, we're going to be able to talk about locations without talking about how far to go left and right and how far to go up and down, because that can be kind of restrictive. And even if you think about it in the real world, if I tell you where something is, it's not always that we talk about how far you need to go, say, east and west, and how far you have to go north and south. I mean, I can tell you, all right, so from here, you're going to have to go 5 miles west and then 6 miles north, right? We can describe things that way. But more often, I say, oh, you got to go 2 miles that way, right? I give you a distance and a direction, right? Think about how often you do that, right? You're at the Y, someone asks you, where's state line? And you say, oh, you just go that way a couple miles, right? We do that all the time. And so mathematicians went, hey, you know what? Maybe we should do the same thing. Instead of describing everything as a left and right and up and down, maybe it's a how far away you are and what direction you need to go. Okay, so that's what we're going to do today. And we call these things polar coordinates. Okay, so the topic of today is polar coordinates. In terms of sections, I can just tell you this because I just looked at the section numbers. This is 10.3 and 10.4 if you're playing along at home. So let me go to the board and kind of show you what's going on.
All right, so I'm going to go ahead and draw the coordinate plane like you're used to. Okay, so we're going to go ahead and just draw this like you're used to with our X's and Y's. But instead of labeling a point in terms of its x and y, right? Like we could, that this point, let's say it's right here, is x comma y. You guys know that in rectangular coordinates, what that means is that we go over here a distance of x, and then we would go up a distance of y, right? And so obviously if there are minuses, we're just going the other direction. All right, well, now our thought process is, instead of this left and right, let's just say starting at the origin, I tell you what direction to go, and I tell you how far away it happens to be. Okay, so what I'm interested here is this distance that I'm going to call r, and then this angle, because remember, angles really do kind of give you an idea of direction, tells you which direction to head. So in polar coordinates, the idea is, instead of x's and y's, we're going to use these r's and thetas. So the corresponding point in polar would be written as r comma theta. So that's the idea. It's not really that big of a deal, and it should make sense because, like I said, in the real world, we do this all the time. Okay, so let me just play around with this a little bit. Let's take a couple of points in polar and let's plot them, just so you can get the feel for how this works. So let me start with a new coordinate plane here. And let's plot some points. All right, so for example, call this guy A. Let's plot the point 2 comma 3 pi over 2. All right, so you got to think about this a little differently now. That first number is our distance away from 0, from the origin. So we're going to go out 2 steps. So basically, you tell me what direction to go, I'm going to walk out 2 steps. Now, the next number tells us what direction to go. And these are the same angles as in standard position. So think about where this would be. We're going to go to an angle of 3 pi over 2. So starting at 0, we come around here to 3 pi over 2. That's the one pointing straight down. And we would go 2 steps down. So I'm going to go ahead and just put a couple of tick marks on my graph here so that we can address these later. But here would be the point 2, 3 pi over 2. Now, obviously, in rectangular, we would use different coordinates, and the coordinates for this one in rectangular would be 0 comma minus 2. So I'm going to go ahead and write underneath each point what the corresponding rectangular coordinates are, at least for ones that are pretty easy for us to figure out. For those that aren't, we'll figure them out later. All right, so cool. 2 comma 3 pi over 2. How about this point? What if we had the coordinates 1 comma 3 pi over 4? So again, this is telling me go 1 step. Once you tell me what direction to go, I'm going to go 1 step. And in terms of what direction, I'm going to go in the direction of 3 pi over 4. Okay, well, 3 pi over 4 would be that angle, right? 3 pi over 4. And what I'm going to do is I'm going to go out 1 step. So let me take the same distance, mark myself out 1. So this would be point B. It'd be 1 comma 3 pi over 4. So I go in the direction of 3 pi over 4, a step of 1. Well, this one, I can tell you what the coordinates are pretty easily because this is on our unit circle, since I'm a distance of 1 away. And 3 pi over 4, I know the sine and cosine of that. But that's actually the point minus root 2 over 2, comma, root 2 over 2. And I'll show you in just a minute how you can figure out what the rectangular equivalent is. instead of having to try to rely on our memory. But that would be the point 1, 3 pi over 4. So let me give you another one here. Let's call this guy point C. And let's go 0, 7 pi over 6. All right, so again, that's an R and a theta. It's a distance and a direction. So we're going to go in the direction of 7 pi over 6. And we're going to go 0 steps. All right, so where are we? Yeah, thanks, Aris. We're at the origin. This right here is C. It's the equivalent of 0, 0. Right? And here's what's kind of interesting about the origin is that clearly we could describe that in lots of different ways. What could I do to this point that's in polar, so the black one? What could I do to that so that I'm still at the origin? What could I change? All right, so like the error just said infinite angles. Yeah, I can pick any angle I want. Give me any direction, right? Point your finger in any direction and tell me take 0 steps that way. I'm still going to be at the same place. All right, so here's something that's a little bit quirky about polar angles or polar coordinates is that there's not a unique way to describe a location. There's more than one way to describe any location. So let me just go ahead and write that down here. So there's more than one way to describe a location. I'll call it describe a point. And this is new. In rectangular, there's only one way. There's only one way to tell me how to go left and right and up and down to get somewhere. But in polar, there's going to be more than one. And in fact, can you tell me another way of describing point A? Can you change the angle instead of 3 pi over 2? Can you give me another angle that would bring me to that same point? Okay, so William, you just said 270 degrees. That's cool. I was looking for more just radians, not just the decimal equivalent, but Adam, you just threw out there 7 pi over 2. Yeah, perfect. 7 pi over 2, that's going to be a whole loop and this more. But 7 pi over 2 points in this direction. So does minus pi over 2. So does anything else. And so you can even see that if we're not at the origin, there's still more than one way to describe the location of a point. All you have to do is change that angle so that it's another one that's coterminal. So this is one of those things that will make polar coordinates a little bit more complicated, and that there isn't just one way of describing the location. It also means, like, if I give an exam, I could ask you guys to give me coordinates of a point in polar, and every single one of you could give me a different answer and still be 100% correct. So kind of weird, for sure, but yeah, that's where it is. All right, so let me do one more point, and then we'll get to the how do we do the conversions. And this one, I'm going to do, let's do, call it D, getting kind of cluttered here. Let's go with D being -1, and let's say 2 pi over 3. No, 4 pi over 3. So let's see if we can figure out where that is. All right, so again, it's got an r and a theta, and we see that the theta is 4 pi over 3, so that tells us the direction to go. I'm going to go ahead and plot that. So here would be 4 pi over 3, somewhere down there. And now what this is telling us is that we need our r to be -1. Now, the way I told you about r, this probably feels really wrong, because I told you r was how far to go in the direction that they tell us, right? Go that way, 4. All right, well, now I'm saying go that way, -1. Well, you guys have seen enough math. What do you think that means? What do you think a negative r does? How about this? What's a negative x tell you to do as opposed to a positive x? Or a negative y as opposed to a positive y? Okay, so you just said different quadrant. Yeah, it is going to bring us to a different quadrant. It's going to tell us just basically go backwards. Yeah, go in the opposite direction. That's really all negatives are. If you haven't kind of caught that yet in math, negatives are just telling us go the opposite way. And so a -1 tells us, okay, actually what we're going to do is we're going to go the opposite direction, 1. So that would bring us up to this point right here. So it's still 1 step away, just in the opposite direction of 4 pi over 3. So it is totally fine to have negative r's. You can have negative thetas, just like you can have positive and negative x's and y's. We just have to remember what they mean. Negative thetas just tell us go in the opposite direction when we rotate. And negative r's tell us go in the opposite direction when we're leaving the origin. All right, so kind of making sense, I hope a little bit. All right, well, anyway, so that's the idea behind polar coordinates. Now, obviously, to make this work a little bit better for us, it'd be nice to be able to kind of bounce back and forth between them, because you don't know the polar as well, obviously, because this is brand new. And it turns out that there are really easy conversions to go from one to the next. And all of it comes back to this picture. Okay, so let's look at the 2 different ways of doing this. The one is given polar, find the rectangular. So that means given an r and a theta, how do we find x and y? Okay, well, let's just look at this picture and talk about finding x. If you know r and theta, but you want to find x, what would you do? Like if I gave you this triangle and I said, okay, this length is 4 and this angle is, pi over 10, how would you figure out x? So I don't know if it's just nobody's out there, you're quiet today. Thanks, Adam, appreciate that. Yeah, so find cosine or sine. Yeah, we'd use cosine. We know that cosine is x over r, right? Like from this picture, we know that cosine of theta is equal to x over r. So if I want x, I just would have to take r times the cosine of theta. So if I give you an r and a theta, it's really easy to find x. It's just r times cosine of theta. I also want to point out that you've known this since week 1. Week 1, go back to April. And this was one of the very first things we did. Remember when we talked about the unit circle definition? The x-coordinate was the cosine of the angle. This r factor just allows for not being on the unit circle. So then similarly for y, instead of cosine, it's going to be sine, because the y-coordinate is the sine of the angle. So there are your conversions from polar to rectangular. Given a pair of polar points, you just put it into this and you'll get your rectangular versions. Okay, so then what about going the other way? Given rectangular, how do we find the polar? So that means given x and y, how do you find r and theta? So look at this picture. Now we're given the red numbers and we want to find the black ones. So let's start with r. How would you figure out what r is? If you know x and y, how do you find r? All right, thanks, Adam. Pythagorean theorem. Yep, something that you've known even longer than April ago. We know that whatever r is, r squared is going to equal x squared plus y squared. So if you give me x and y coordinates, I can figure out the r value just by using Pythagorean theorem. All right, cool. So then what about theta? What if you want to find this angle knowing x and y? I'll give you another hint. Oh, there you go. Thanks. I got a whole bunch of people now throwing it in there. We're going to use tangent, specifically inverse tangent, right? We know that tangent of theta is going to equal y over x. So you can do the inverse tangent of that to find your theta. All right. So going in that direction is a little bit harder, not going to lie. We're going to have to use the inverse tangent, but we're also going to have to think about this because, as I just mentioned a little bit ago, polar coordinates, it's not unique. There's not one way of representing it. And you can even see that from the equations. Like, think about this one. If I solve for r, I have to take a square root, which introduces plus or minus. I have options. This one, tangent of theta equals y over x. Well, we know inverse tangent gives us one angle, but it's not the only angle that works. We have lots of different options, and that even shows up in here, okay? So when we go from rectangular to polar, we're gonna have to be a little bit careful. We are gonna have to pay attention so that we get the right combination of r and theta. It's not always gonna be a positive r with the theta that inverse tangent gives us. Sometimes it's not even the angle that inverse tangent gives us. All right, so we definitely have to watch out for that. So let's try a couple. Let me just show you how we convert from x and y to r's and thetas and vice versa. But you'll see that it's pretty easy. So I want to go back to one that we did, that we plotted. It was the point D. If you go back and you look at that, we had that point was -1, 4 pi over 3. And let's convert that to rectangular. So let's figure out what the x and y for that point are. Okay, so x, it's going to equal r, so -1, times the cosine of theta. So -1 times the cosine of 4 pi over 3. And y is going to be r times the sine of theta. So the only difference is we make it a sine instead of a cosine. But those are numbers that we know. if you go back and you look at your chart, you see that the cosine of 4 pi over 3 is -1/2. So that gives us an x-coordinate of 1/2. All right, so the y, well, sine of 4 pi over 3, that was -√3 over 2. So -1 times that is a positive √3 over 2. So that point would be 1/2 to the right and √3 over 2 up. And if you go back and you look at your notes where we found that point when we went -1 in the direction of 4 pi over 3, that brought us exactly there. So you can see that those coordinates definitely make sense. So going to rectangular is really pretty easy. I think this is the only example I'm going to show you, because I'd rather spend our time talking about going from rectangular to polar, because that one gets a little bit more tricky. All right, so let's do a couple of those. So here's your next one. I'll leave those conversions here for a second as long as I can. All right, but it's just Pythagorean theorem and inverse tangent. All right, so let's go the other direction. Let's take the point, say -2, comma 2√3, and let's convert this to polar. So I just gave you an x and a y. So we're going to find r and theta using these conversions. So r squared, that's equal to -2 squared plus 2√3 squared, which is 4 plus 12 or 16. So I've got r squared is equal to 16. So in terms of my choices for r, I'm going to go ahead and put it plus or minus 4. So when we describe that location, we can use either +4 or -4. Obviously, those will lead to different angles, but we know that it's either 4 or -4. All right, so there's r. We're going to have to pick from that. But then let's go and do tangent. So we know that the tangent of theta is equal to y over x, so 2√3 over -2. So we get that the tangent of theta is -√3. So let's think about all of our different options there. So you use inverse tangent on this. Inverse tangent is going to give us -π/3. So you can use your calculator, or remembering that this is going to give you the fourth quadrant angle, blah, 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 right? So you get -π/3. But that's not the only option. We have to add on pi times n. So there are an infinite number of thetas that we can use. We already knew that. We already kind of saw that. But there are two different r values that we can use. So really what we have to do is match them up properly. Pick an angle and then figure out what corresponding r we would use. Or pick an r and then use that corresponding angle. Now, this is a little bit tricky for sure. So what I recommend you do is draw the picture. Think about where that point is. So if we go back to the original -2, 2√3, that tells us that we're over here. Right, we're left 2 and we're up 2√3, which is like 3.5 or something like that. So we're left 2 and up 2√3. And the reason I do this is it helps me see which r's go with which thetas. So for example, let's just pick that theta. let's say we use theta equaling minus pi over 3. So that's the one that the inverse tangent gives us. Which value of r would we use? Plus or minus 4? All right, thank you, Mariola. Now, William, all right, so yeah, we're going to use the negative. So this would be minus 4, comma, minus pi over 3. Because minus pi over 3 points down here in the fourth quadrant. I don't want to be in the fourth quadrant, so I got to go the opposite direction. Okay, so I'm going to put or, because here's another way we could represent that point. What if I went with a positive r? So what if I chose, I want r equaling 4? What angle could I use now? Because it certainly isn't minus pi over 3. And you have lots of choices. Okay, so we go ahead and add pi to it, and we get 2 pi over 3. So cool, thanks guys. So we get 2 pi over 3. That would be one of the options, but that definitely points in the right direction. 2 pi over 3 points up here, and now I go out my 4 steps. All right, so like I said, this one, we have to be kind of careful. We really got to watch, because if all you do is just take the inverse tangent number and the positive r, in this case, you'd be wrong. So you got to watch out for that. And don't think of this as, oh, math teacher is getting tricky. No, it's just like the way that polar coordinates work. Since there are an infinite number of ways of representing a point, we got to watch it. We got to be careful. All right, well, that's how polar coordinates work. Hopefully that kind of makes sense. And really, it's just going to be a matter of using those conversions to bounce back and forth. Okay, let's take a real quick break.
All right, so now that we've seen how to convert specific points, let's look at converting equations. Because if I give you an equation in polar, you may not really see what it does, what it looks like and all that. But it might help if it was in rectangular, and vice versa. Sometimes rectangular equations can be written in a much easier form if we go to polar. So let's do some more of this conversion, but let's attack equations. So let's go back to the board.
All right, so this is all going to come back to those same equations, conversion forms. So let's remind ourselves of those. I'm going to try to keep them up here on the board, but because I'm in really limited space, I might ditch them at some point. So we've got x is equal to r cosine theta, y is equal to r sine theta. And then again, the conversions the other way are Pythagorean and the tangent. Okay, so I'll try to remember to keep those up here. All right, so what we're going to do then is let's play around with some of these and go convert the equations. All right, so I'm going to start with some rectangular and show you how we can convert rectangular equations into polar equations. They're actually pretty straightforward. So, for example, let's say we had something like 3x plus y equals 2. So that's a rectangular equation, and you know what that looks like, hopefully. That's just a line. Now, if I want to convert this to polar, So that's what we're going to do here. Let's convert this into polar. What we're going to do is just replace the x with an r cosine theta. So we get 3 times r cosine of theta. We'll replace the y with an r sine theta equals 2. Now, I will tell you that just like with rectangular equations, you know, with the rectangular, we try to write them as y equals. Well, with polar, we try to write them as r equals. So let's just do a little bit of work on this to solve for r. I'm going to factor it out since there's an r in both places. And then I can divide by that entire factor. And so here is the polar equivalent of 3x plus y equals 2. And I can imagine that most of you are looking at this right now and going, what the, seriously? Why are we doing this? This is ugly. Like compared to the nice simple linear equation, this thing is all gnarly. And yeah, this is not the kind of thing that we use polar for. We don't use polar for lines, but I just wanted to give you an equation that was pretty easy so you could see the process of how we plug it in. And so this rectangular equation ended up looking pretty bad once we turned it to polar. But let me show you examples where that's not the case, where if we take something that's rectangular that looks kind of rough, it ends up being kind of nice. So here's another one, and you may actually know what this is. Let's go with x squared plus y squared equals 4. So that's another pretty common graph. Do you guys recognize it? Yeah, that's right, William. It's a circle. It's a circle who's centered at the origin. It's got a radius of 2, but no big deal, right? So it's a circle. But watch what happens when we go to polar. So again, I'm going to replace my x and my y with the r cosine and r sine. So we're going to get r cosine theta squared plus r sine of theta squared equals 4. So this will give me r squared cosine squared theta plus r squared sine squared theta equals 4. So remember the trick we pulled last time? We factored out the r. Well, let me do that here. Let me factor out the r squared. So I get r squared times cosine squared plus sine squared equals 4. And hopefully by now, you got triggered when you saw cosine squared plus sine squared. And I don't mean triggered in a bad way. All right. Hopefully you went, ooh, that's Pythagorean. Cosine squared plus sine squared is actually just equal to 1. So this gives us r squared equals 4. And of course, we can solve that for r by taking the square root. And so we get r equals 2. So check that out. This, r equals 2, is the polar equivalent to x squared plus y squared equals 4. So this shape, this circle, specifically has a really nice form when it comes to polar. It's just plain old r equals 2. So sometimes polar equivalents are really, really nice. And they tend to be the ones that have some kind of curvature to them, things that are circular, elliptical, stuff like that. Their polar forms tend to be pretty nice. And really, this is the process. This is how you go about and you find them. All right, so going from rectangular to polar, it's just a matter of plugging in for your X and your Y. Sometimes you can do this faster, like this one, for example. I want you to notice that we could have done this a little bit quicker if we had recalled the conversion the other direction. We already knew, if we look up here at the top, that x squared plus y squared is equal to r squared. And so we could have saved ourselves a little time if we had recognized that and jumped straight from x squared plus y squared equals 4 to r squared equals 4. So keep on the eye, or keep on the lookout for that. Keep your eye out for that. That if we've got like a tangent of theta, you can immediately replace it with y over x or vice versa. And the same thing with x squared plus y squared, we can make that r squared. All right, but again, just like going from rectangular points or getting the rectangular points, these are pretty fast. Converting to polar, really simple. You just plug these things in and you go. It's going the other direction that sometimes takes a little bit more and requires us to be a little bit more creative. So let's do a few of those. Let's go the other way. All right. So for example, let's say we had something like r equals 4 secant of theta. Okay, so real quick, let me jump back. Sorry, I just noticed, Bella. So that r squared times cosine squared plus sine squared is equal to r squared times 1, exactly, because of the Pythagorean identity. Sine squared plus cosine squared equals 1. So anytime we see that expression, we can replace it with 1. So we get r squared times 1, which is r squared. All right, you're welcome. And that actually brings back a point about identities. That's why we actually want identities and use them, is because they can simplify things later. And this is a great example of where things got simplified a great deal by making use of the Pythagorean. Okay, so let's jump back to this one. So we're going to have r equals 4 times secant of theta. All right, so going the other direction is definitely more complicated. Because think about this. I don't have something that just says r equals. And even if I did, that r is going to equal some square root of x squared plus y squared. That's not nice. Similarly, I don't have something that theta equals, and even if I did, it'd be an inverse tangent of y over x. So then I'm going to have to take a secant of an inverse tangent, and it's going to be horrible, right? Well, the trick with these, for sure, is to actually use the other conversions. Use the cosines and the sines with our x and y. Let me show you how this would play out. So right now I've got secant. I'm going to change that. I don't want secant. I want cosine. So if I were to rewrite this, this is the same as 4 over cosine. All right. So now what I can do, actually, I'm going to multiply both sides of this by cosine. So we'll just go ahead and multiply left and right by cosine of theta. So we've got r cosine theta is equal to 4. And this r cosine theta, if we look up above, notice that that is the conversion for x. So this guy, r equals 4 secant of theta, it's actually equivalent to x equals 4. So we found this basically by, well, going back to sines and cosines, and then using the substitutions for rectangular to polar. So interestingly enough, the rectangular x equals 4 is the same as the polar r equals 4 secant theta. So this graph, the graph of that's a vertical line. So this vertical line translated into polar is much more complicated. But like I told you, things in polar, they tend to work best for curvy objects. And a line is very not curvy. But we're going to pull all kinds of tricks like this, where we end up actually using the other conversions to help us. So let me show you another one. I'm going to need more space, so I'm going to start back up here. All right, so let's try this. Let's say that we've got r equals 6 sine of theta minus 2 cosine of theta. And again, let's convert this back to rectangular. Let's get this in terms of x's and y's. All right, well, we already have sines and cosines, which we saw was useful, making use of these. But notice that what I'd really like to have is r times cosine and r times sine. And right now I don't have that. I have just sine and I have just cosine. But I can get r times that if I multiply by r. So I'm going to multiply both sides of this equation by r. So this gives me r squared equals 6r sine theta minus 2r cosine theta. And now I have exactly the conversions for x and y. R sine theta is y. R cosine theta is x. So we get r squared equals 6y minus 2x. So while I'm not done because I still have r's, but notice that I did get rid of all of my thetas, which is definitely a good place to be in. All right, well, now we got to get rid of that r. All right, well, r squared, we're going to make use of the fact that we know what happens with r squared. Look at our other conversion. R squared is actually equal to x squared plus y squared. So I'm going to replace that. And so this is the rectangular equivalent of what we started with. So is that one better, worse, uglier, nicer? I don't know. It's a little subjective. But that is the rectangular form, which some of you may be able to recognize. Do you know what that is? What the graph of that is? All right, so we just said ellipse. I was going to give you a hint when I just say go ahead and cut and paste, because it's also a circle. It's a circle because of the fact that the coefficients on x and y are the same. So it's a circle. It's just centered somewhere different than the origin. You'd have to complete the square, do all that to figure out where its actual center is. But yeah, so that's the rectangular form of that polar equation. So keep these tricks in mind. The multiplying by r, that happens a lot when you have sines and cosines. The converting them into sines and cosines if you're given things like secant and cosecant and stuff like that. But basically you can get, you can convert these things and get their rectangular forms in this way. All right, let's do one more, just so you can kind of see how this plays out. Let's try It's not going to actually be terrible looking at start, but let's go with this conversion. Let's see if we can change r equals 3 cosine of 2 theta. All right, so this is actually a very well-known shape. Probably not to you guys yet because you haven't seen the polar yet, but we'll talk about this next time. It's actually called a rose because it looks like a flower, looks like it's got petals. So this is a rose. It's actually a 4-leafed rose or 4-petaled rose. But regardless, let's see if we can convert this back to polar or to rectangular. All right, well, obviously the big issue here is the cosine of 2 theta. Having the 2 in there makes things a little bit more complicated. So let's get rid of that. Let's actually use the double angle identity for cosine. All right, well, if you look at that, you'll notice that there are 3 forms for the double angle cosine identity. So let's pick our favorite. I don't really have a favorite, so I'm going to go with just the one that's got the cosines. So it's the first on our list. Actually, no, I think the first on our list is the cosine squared minus sine squared, but I'm just going to go with the first one. So we're going to have r equals 3 times 2 cosine squared theta minus 1. So if I distribute that, I now have 6 cosine squared minus 3. So this is still in polar, but at least we're down to just a single theta in our angle, or as our angle. We don't have the multiple angleness. But now I want to get rid of those cosines. All right, well, let's make use of the x equals r cosine of theta. And so let's multiply by r squared. Now, the reason I'm doing r squared this time is because I've got a cosine squared, so I want 1 r to go with each of those. So this will give me r cubed equals 6 r squared cosine squared minus 3r squared. Let me just rewrite this real quick. The r squared cosine squared is the same as r times cosine being squared. And now that I can convert. So this is going to be 6x squared minus 3r squared. So we have gotten rid of the thetas. Now all that's left is to get rid of the r's. Well, let's look at this r squared real quick. So r squared, we know that that's equal to x squared plus y squared. So let's put those in. And I can distribute and simplify that a little bit. That ends up giving me 3x squared minus 3y squared. Because with the x's, I've got 6 of them minus 3, so leaves me 3x squared. So I'm going to run back up here because I'm out of space. But where we are now, like we're getting there, home stretch, right? Almost all of the r's are gone. Okay, but I'm left with that r cubed. Well, here's what we're going to do. The r, we know what r squared is equal to, but we can actually get r by taking the square root. And so this is going to be the same as the square root of x squared plus y squared cubed. So where that square root came from was just that original Pythagorean. And so Bella, you just threw in fractional exponents. Yeah, that's exactly what we would do here. The square root is a half power. And when you cube that, that gives you 3 halves. So this is the same as x squared plus y squared to the 3 halves equals 3x squared minus 3y squared. And I'm going to go ahead and put a box around that because that's as far as we're going to go with this for right now. I mean, you could manipulate it a bit algebraically if you felt like it. But I just wanted to get to a point where we eliminated r and theta. Okay, well, let me remind you what the other one looked like. It was r equals 3 cosine of 2 theta. And I think that most of us would be pretty okay with saying this polar form is nicer than that rectangular. And when you see the graph of this thing, when you see what it actually looks like, you'll go, yeah, I can see why polar is better because it's definitely curvy. All right, so the moral of the story here is that you can always go back to rectangular by using the conversions, but you don't necessarily want to do that. It's not necessarily going to be beneficial. It's not going to necessarily give you what you want. And sometimes it's worth it just to stick with the polar. All right, and that's why we want to get comfortable with polar, what it means and how it works. All right, so any questions on that one?
Okay, well, hearing none, then I'm going to go ahead and kind of move on. All right, so I think that's going to be it for today in terms of polar coordinates. We're not going to do anything anymore that's new. So what we can expect on Monday, or not Monday, on Wednesday of next week, we will continue our conversation of polar. I want to talk about the graphs, what graphs look like and all that. And that should be sort of a fun day because we'll draw all kinds of pretty pictures and we'll use technology to help us. We'll do a couple of plot pointing, like, you know, draw the different dots and then connect them. But then we'll make use of the technology because let's be real, that's what you would do if you were presented with one of these out in the real world. So that's what we'll do on Wednesday. But on Monday, we have our third and final regular exam. Right, so we'll have that, and then a couple weeks later we've got our final and we're done. So we're definitely in the home stretch. I think we've got 2 more weeks of class and 1 week of final left, but who's counting, right? So in terms of what's going to be on the exam, format's going to be the same like you're used to. I will turn it on at the beginning of our usual class time. So it will be on Canvas and available starting at 11 o'clock. You'll have the 2 hours to take it and then the extra half hour to deal with technology issues and all that. So it will need to be submitted to me by 1:30. But in terms of what's going to be on it, it's going to be on sections 9.3 through 9.5. And I'll post something on Canvas with all this information as well. But it's 9.3 through 9.5. So that's the identities after the basic ones and the sum and difference of angles. So even though I'm telling you it's 9.3 through 9.5, you really need to know all the identities because we still use all the identities in these subsequent sections. But so basically it's the identity stuff. So think back to that quiz, the most recent quiz you guys took. So things like that. So double angles, half angles, product to sum, sum to product, power reduction. So all those kind of identities. There will be questions that ask you to confirm identities. There will also be ones that ask you to use them, right? So know the identities, but then also in there was the section on solving equations. So also expect that. Expect solve the given equations. So in there, some things to review for sure. Other than the trig, go back and review your algebra, factoring, fractions. Those are the two primary algebraic things that we use. So go back and look at those. Also, and I'm kind of glad, I think it was Juan who asked me about that homework problem that had us solve something that had cosine of 3x. Don't forget about those, that when you've got more complicated stuff inside the trig function, we still solve it like normal. Isolate the trig function, find the angles. Make sure you put on plus 2 pi n, except with tangent and cotangent, put plus pi n, because that catches all of them. And then if I ask you for some specific ones, you can find them. So be sure you look for that too on the exam. What am I asking you to find? Am I asking you to find all the solutions? If it says find all the solutions, got to have that 2 pi n business. If I say find all the solutions from 0 to 2 pi, okay, well, find all the solutions from 0 to 2 pi. So just watch out for that. I know sometimes when we take exams, we get into just autopilot and you're just going, you're going, you're going, you're going, you're going. And we don't really pay attention to directions. So specifically with equations, watch that. Okay, so pretty much chapter 9, technically 9.3 through 9.5, but then it's also going to have on it 10.1 and 10.2. And those are the sections on solving triangles. So the law of sines, law of cosines, those kinds of things. So expect also some questions on this exam that are in this triangle. A is 4, beta is 62 degrees, gamma is 9 degrees. Solve the triangle, right? So expect those kinds of things. Along those lines, don't forget about the side-side angle, ass backwards. That's the one that's going to give you possibly more than one, right? So we got to make sure we watch out for that. If you run into one of those situations, I'm going to expect that you give me both triangles. And if you run into a situation where no triangle exists, obviously that's going to be a perfectly fine answer. You're going to say, hey, no triangle exists with this information. So there will be all kinds of those with different combinations of quantities. So make sure you practice law of sines and law of cosines. And then also in there were the areas, the different area formulas. So make sure you know how to use those. Because I'll probably put something on there where you have to find an area. And then the last thing with those sections is that that's where some applied problems can come in. Like remember, we were trying to figure out how far it was across the river, things like that. Those kinds of problems might show up as well. All right, so that's the content. 9.3 through 9.5 and 10.1 and 10.2. But make sure you know the identity stuff from 9.1 and 9.2 as well. So Juan just said what section was areas. That was 9.2, I believe. It might have actually been split up amongst them, but it's somewhere in the 10.1 and 10.2, I think 10.2. Honestly, I don't really pay attention to where stuff is. I just teach the stuff. And so I know I kind of, do this in between sections. So, but definitely go back and look at 10.1 and 10.2. That's where they'll be. All right. So there's your exam. And then Era's just reminded me I need a word of the day. And let's see, I've already used that one. Oh, okay, here we go. So the word of today is going to be schedule. This was the spring college schedule. So word of the day is schedule. Schedule. Thanks for that reminder. All right, so I think that's everything I've got for you. Any other questions from you guys before we sign off? So Mariola, some extra time on chapter 9 homework? You bet. Let's say I extend it to Friday. 2 more days. Sound good? All right, we're getting some pretty much cheers for that. So let me just write myself a note. I'll try to take care of it as soon as we're done with the class. Otherwise, I'll forget. But so chapter 9 review. Let me make it due Friday. Okay, so I'll go ahead and do that. Anything else? All right, so you guys have a great weekend, and I will not see you Monday because we'll be doing the exam, but realize that I am around. I do have office hours, so any questions, feel free to reach out on email or come pop in during office hour. So other than that, have an awesome week, and I'll see y'all Wednesday.